part 2 now we're going to be focusing more on the unsaturated hydrocarbon compounds. So these are primarily going to be the alkenes. We'll also have a brief look at other unsaturated hydrocarbons like the alkynes and also benzene. So we'll see that the properties of these unsaturated hydrocarbons are quite different to what we saw for the saturated ones. In general, they're more reactive and can participate in more chemical reactions for that reason. So we've got our alkene functional group, and the characteristic of the alkene is that it's going to contain one or more double carbon-carbon bonds. Likely also to contain single carbon-carbon bonds, but it has to have at least one double carbon-to-carbon bond to be classed as an alkene. So for the naming convention, whenever we have a compound with ene at the end of the name, we know it has to be an alkene. So the example we have here is propene. And here is the propene structure. So you can see that double carbon-carbon bond between the first two carbons here, and then a single bond to another carbon here as well. So that's what we mean by the combination of double and single. It doesn't have to all be double, just one, and then we classify it as an alkene. So let's remember where the alkene sits in comparison to our other groups. So the alkane had single bonds and the alkyne has triple. So the difference between these and our alkene is the fact that we've got that double carbon-carbon bond in the structure there. So we did see an alkene in the previous lecture when we were looking at stereoisomers. So the structures down the bottom here are actually alkenes because they have the double carbon-to-carbon bond. So when we have this arrangement with the double carbon-carbon bond, if we had the CH3s both pointing on the same side of that double carbon-carbon bond, we called this the cis version of the stereoisomer. And then if one of the carbons was on one side and one on the other of the double bond, then this was the different arrangement or the trans arrangement. So in general, we have the unsaturated hydrocarbons being more reactive than saturated ones. And this comes back to the bonding between the carbon atoms within these structures. So for an alkane, it only had the single carbon-carbon bonds, and a significant amount of energy input is actually needed to break these bonds. So because so much energy is needed to break the carbon-carbon bonds within the alkane structure, it means it's actually quite difficult to replace either the carbon atoms or the hydrogen atoms within this structure. And that gives the alkane the property of being stable and unreactive. So let's compare that to an unsaturated hydrocarbon like an alkene or an alkyne that have these multiple carbon-carbon bonds. So because of the presence of that multiple carbon-carbon bond, a smaller amount of energy is actually needed to break one of the carbon-carbon bonds within the structure than compared to breaking a single carbon-carbon bond in an alkane. And the important part of this is that once one of the multiple carbon-carbon bonds has been broken within one of these structures, then new covalent bonds can be formed to different atoms to make sure all the carbon atoms in the structure have 4 covalent bonds to give it that full valence electron shell. So here we can see some examples of hydrocarbons with multiple carbon-carbon bonds. So you can see an alkene on the left-hand side here where we've got the double carbon-carbon bond, and an alkyne on the right-hand side here. So we can see by looking at these structures that they have less hydrogens attached than the alkane variant. Even just comparing the alkene to the alkyne, which one has more hydrogens attached? Is it the alkyne or is it the alkene? Well, the alkene actually has more hydrogens attached. So we've got an extra 2 that I'm putting the boxes around on the left-hand side that we don't have on the right-hand side. So why is it that the alkene has these 2 additional attachments to hydrogen, whereas the alkyne does not? Well, it's to do with the number of carbon-carbon bonds. So because the alkene has a double carbon-carbon bond, there's still room for these extra two hydrogens to make up the bonding arrangements to 4 for each carbon. Whereas for the alkyne, the triple carbon-carbon bond means that each of these carbons only needs to form one other covalent bond. However, what you can do to one of these structures is actually break one of these multiple carbon-carbon bonds and make more space available for other atoms. So for example, if we had a triple carbon-to-carbon bond like this, then initially there'd only be room for one additional attachment to hydrogen. But what about if we broke one of those bonds? So if we broke a carbon-to-carbon bond, then we'd only have 2 carbon-to-carbon bonds. So we're down to what you'd see in an alkene. So we've transitioned from an alkyne to an alkene by getting rid of one of those double carbon-carbon bonds. So how many bonds does each of the carbons have in this structure down the bottom here? They've got 1, 2, 3, and this one also has 1, 2, 3. So what that means is there's actually room for each of these carbons to form a bond to another atom. So by removing one of those carbon-carbon bonds, we've actually made space to add new atoms in. So depending on what the atom is or group of atoms that it's reacting with, then something can be added in this position. I've just added in as an X, showing that can represent lots of different atom types. But essentially, this demonstrates something that will be very important in this next section of the lecture, that if you break a carbon-to-carbon bond, that means you can add new atoms into bonding positions with those carbons that were previously part of that multiple carbon-carbon bond. And every time we break a carbon-to-carbon bond, that means we've got 2 new bonding positions, one on one carbon and one on the other. And those 2 new bonding positions are exactly the reason why the alkene can actually attach to these 2 extra hydrogens compared to the alkyne, which can't. As you remove these multiple carbon-carbon bonds, there's more space for other atoms to bond. And that's the basis of a lot of the reactions that we're going to look at in this section. So let's have a look at an animation of the alkene and why it's considered to be quite reactive. So we've got an energy input here to start the reaction. So remember, the energy input is going to break specific bonds within these compounds. So the bond that's going to be broken is one between the carbons here. So one of the multiple bonds here within that double carbon-carbon bond will be broken. We're also going to break a bond between the 2 chlorines here. So once that occurs, we've got atoms that need to form additional bonds. So this carbon, and both of these chlorines now don't have the right number of bonds. So what are they going to do? They're going to rearrange into a way that means all of the atoms involved have the right numbers of bonds. And they do this by attaching together. So the purple here represents a new covalent bond formed between the carbon and the chlorine. So we've got 2 new attachments here. And where did they attach? Well, it was the position where we had the 2 carbons. So each of these 2 carbons that did have that double carbon-carbon bond, after it was broken, they were able to take on additional atoms. And that's what I was showing you on this previous slide, where by breaking one of the bonds between the carbons, we've now got 2 extra bonding positions. So let's watch that once more. Starting off with the double carbon-carbon bond, break it with an energy input, quite a small energy input, and then that means we can go ahead and add new positions, new atoms into those bonding positions by forming new covalent bonds. So you might remember back to when we were looking at the alkane reacting with something like chlorine, we could only add 1 chlorine atom at a time. But because the alkene is more reactive, we can actually add 2 chlorine atoms at once in this type of halogenation. So essentially, what's happening here is once the double bond is broken, then the 2 chlorine atoms can be incorporated into the compound by forming new covalent bonds, ensuring that each carbon still has the 4 covalent bonds it needs to be stable. So there are different types of chemical reactions that follow this same pattern where one of the bonds within an alkene is going to be broken, one of those multiple carbon-to-carbon bonds, and that allows new atoms to be added in its place. And we can see that in the description here. So once one of the multiple carbon-to-carbon bonds present in a double or triple bond is broken, then the carbons that were previously involved in that bond have new bonding positions that can attach to new atoms. And the reason we do this is to ensure that each carbon has those 4 covalent bonds it needs to be stable. So essentially, by breaking the old bond between the carbons, we can then have new bonds being created, which is what is described here in red. So we're going to have a look at 3 different variations of this reaction. Hydrogenation, where the reaction is going to be between an alkene and a hydrogen molecule. Halogenation, which is similar to what I just showed you on the previous slide, where the alkene will be reacting with a halogen such as chlorine or bromine, and then a hydration. So remember, hydration means adding water to something. When you hydrate, you're drinking water, so it's a good way to remember it. And in that case, we're going to be reacting a water molecule with our alkane. So you can see from this table that the reactants are actually getting converted into a new product through each of these reactions. So this is a nice summary table to look back at once we've been through the details of each of these reactions. So the first one we're going to look at is a hydrogenation reaction. So the name of the hydrogenation reaction gives away what's happening. It's actually got hydrogen in the name. So a hydrogenation reaction is actually a reaction where hydrogen is being added. And what's happening here is the double bond within the double carbon-to-carbon bond within the structure is actually being broken. So one of those carbon-to-carbon bonds will no longer be there, and that means there's now new positions for hydrogen atoms to be added into. So this is following exactly the same pattern as I showed you in that previous animation, but instead of adding chlorine atoms, we're adding hydrogen atoms. And the end result of this reaction is that we're converting a compound that was an alkene into an alkane. Because in the course of the reaction, what are we doing? We're breaking the multiple bond, which is what made the compound the alkene to begin with. So once the compound no longer has the double carbon-carbon bond, it's no longer an alkene. It actually becomes an alkane. And we can see that down the bottom here. The reactant propene has the double carbon-to-carbon bond, but the product, which is propane, no longer has the double carbon-to-carbon bond. It's a single bond here, so that's why we classify it as an alkane. And we can see what's reacting with the propene to make this possible. We've got a hydrogen molecule. And we can see these hydrogens are what forms new attachments to the carbons that previously participated in that double carbon-carbon bond. So let's have a look at another animation to see how this happens. So it's very similar to the previous animation that I showed you. The only difference really is this time we're doing a hydrogenation reaction. So it means that hydrogen is what is reacting with the alkene, and that ultimately means it's hydrogen that will be forming new bonds to the compound. So we follow the same pattern. The first thing that happens is an energy input to break specific bonds within the compounds. And in this case, it's breaking one of the bonds within the double carbon-carbon bond and also the bond connecting the two hydrogens. After this occurs, we now have the freedom of the hydrogens to move about, and also we have 2 carbons which need to form additional bonds. So which are the 2 carbons that need to form the new bonds in this structure? Well, if we count the number of attachments that each one has, this carbon on the left-hand side here has 1, 2, 3, 4 attachments, whereas each carbon on the right-hand side here only has 3 attachments, 1, 2, 3, and 1, 2, 3. So essentially that means that these 2 carbons don't have enough covalent bonds. So how can we rectify this? Well, essentially, we need new atoms to come in and bond to it. Which atoms do you think might come in and bond to these carbons? Well, we're reacting with this hydrogen, so it's likely to be these hydrogens that come in and form the new bond. So let's see if that happens. Yep, so once the hydrogens get close enough to the carbons, they can then form this electron sharing relationship, which is the covalent bond. So now we've created a new compound that has more hydrogen and less double carbon-carbon bonds. It's actually got no carbon-carbon bonds now. So it's no longer an alkene. It's actually now an alkane. So essentially what's happening in the course of this reaction is we're breaking that double carbon-to-carbon bond, and that allows two hydrogen atoms to be incorporated into the compound, ensuring that each carbon atom has the 4 covalent bonds. So let's watch that once more. So we're starting off with our alkene, specifically propene, that has the double carbon-carbon bond. We break one of those carbon-to-carbon bonds, which allows the new hydrogen atoms to come in and bond to the compound. Therefore, now it is an alkane because it has the maximum number of hydrogen atoms and no longer has any double or triple carbon-to-carbon bonds. So essentially what this means is we can use the hydrogenation reaction to convert an alkene into an alkane. So we've actually changed what the pseudo-functional group of our hydrocarbon is. Started off as an alkene and is now an alkane. So let's look at another type of addition reaction. This time, instead of reacting with hydrogen, it's actually going to be reacting with water. Again, it's given away by the name. Hydration basically means adding water. Just like when you hydrate, you're drinking water. So adding water to an alkene, we can call a hydration reaction. So again, it's following the same pattern as we've just seen. We're going to break one of the carbon-to-carbon bonds within the double bond, and it's going to be replaced by new bonds to other atoms. Specifically, in this case, it'll be a bond to hydrogen and a bond to an OH group. So often you see water represented as H2O, but if we draw out its whole structure, it looks like this. There's actually 2 single covalent bonds between oxygen and hydrogen. So because this water molecule actually doesn't need any more bonds, we actually have to break this apart before it can actually bond within our compound, bond to our compound to replace those bonds that were lost. So I'll show you how this happens on the next slide. But essentially the end result of this hydration reaction is to turn what was an alkene into an alcohol containing compound. So it's actually going to have the alcohol functional group. So remember, the alcohol functional group is ROH. We'll be talking about the alcohol functional group in a bit more detail at the end of this session. So if we look at the reaction down the bottom here, we're starting again with propene that has that double carbon-to-carbon bond, and we've got our H2O, which is really represented fully by showing the bonding like this. So after one of the bonds between the carbons is broken, in red here, we're only left with the 1 carbon-to-carbon bond. That means we've got these 2 new bonding positions pointing downwards here that can attach to other atoms. So we can see the OH and the H that have actually been added in have come from the water molecule. So the OH will be coming from this part of the water molecule, and the hydrogen will be coming from the remaining hydrogen that was left over. So that means we actually have to break that bond between the OH and the H within water. So it's quite common for the water molecule to split in this way in chemical reactions, and we'll see it quite often in the course. So of course the OH within the propanol compound is what makes it an alcohol. So through breaking that double carbon-carbon bond, we've made room for this OH within the compound. And remember that OH comes from the water molecule. So let's have a look at an animation of how this hydration reaction takes place, where the alkene is being converted into an alcohol. So again, it starts in the same way. This time we're going to represent water as OHH, which is similar to the representation that I was showing you before, where we've got the oxygen attached to the two hydrogens. So the first thing that happens is we're going to get use an energy input to break some of those bonds. So we get a detachment of the OH and the hydrogen, as well as breaking of that double bond. So let's look at that again. So the bonds that have this energy input lightning strike over it, they're the ones that are going to be broken. So the energy input will break specific bonds within these compounds. So you can see one of the bonds between the oxygen and the hydrogen here is going to be broken within the water molecule, and we're also getting the removal of one of the bonds between the carbons here, which was part of the double carbon-carbon bond. So once we remove those bonds, we then have the freedom of these other atoms to move to the location which is required to form new bonds to the two carbon atoms in this case. So let's look at that again. Once we remove those bonds, then we have the OH and the H moving towards the carbons that need the extra bonds. So why is it that these two carbons need the extra bonds? Well, it's because they no longer have that double carbon-to-carbon bond, so they need to form an attachment to a new atom to make sure they get up to those 4 covalent bonds. So essentially what's happening here is once that double carbon-to-carbon bond is broken, then we have the OH and the hydrogen from water also splitting apart to come and bond to the carbon atoms, and that ensures that the carbon atoms both have 4 covalent bonds. So essentially what's happening here is the hydration is allowing our alkene that had the double carbon-carbon bond to be converted into an alcohol, which does not contain the double carbon-carbon bond, but does contain the OH, which is the alcohol functional group. So remember, wherever we see OH, we know that that means it has to be an alcohol compound. In this case, it's propanol because it's got 3 carbons, so that gives us the prop, and then we have OL at the end of the name, showing that it's an alcohol functional group.